Okay, it's a pleasure to introduce you again, and the title will
I forgot to write it.
ordered in a second.
Yes, today I'm going to talk about symplectic manifolds again, but this time the thing that goes along with it is derived orbifolds. So basically, I had to skip a lecture because I decided to give more introduction. So first I should say thank you for the invitation. I've had a great time the last 3 days. Thank you also for the brilliant person who decided on which rooms to have this in, because the rooms getting smaller, people are leaving, but nonetheless the density is actually great. So thank you all for coming. So I want to start by making a definition of the object that we saw last time. So the definition: a manifold flow category is a category with morphisms M bar PQ, so let's just call it, it's going to be called M bar, that are compact manifold with corners and composition maps M bar PQ plus M bar PR to M bar PR that enumerate the boundary strata. That enumerate the codimension 1 boundary of the target. Okay, which means this is a manifold with boundary. This is the inclusion of codimension 1 boundary stratum. All such codimension 1 boundary strata are given exactly by choice of Q. And the point is that this is what occurs naturally in Morse theory. That's what I explained last time.
Can I just ask, so is there some sort of order, is there some sort of ordering on the points?
It's determined by the existence of a morphism.
Okay.
So if you think about it, the statement that this is compact forces there to be no arrows back and forth, otherwise things will just explode very quickly. So in fact, it follows, for example, that M bar PP is empty, whatever. And so some things will just follow just from compactness. So it's a non-unital category, let me just not say that. Okay, so this is what comes naturally from it. And now, the first thing to say is that, unfortunately, and I also said that Floer realized that we can do some kind of Morse theory on the free loop space of a symplectic manifold in order to study fixed points of some Hamiltonian diffeomorphisms. Fixed points of phi from M to M, which are the time one map of. Again, there's the word Hamiltonian, which I didn't define technically, but it basically means symplectic flows with some small technical condition. Okay? Well, this is a lie. Okay? So he worked out that formally it makes sense, but then when he tried to actually understand what the structure of the moduli spaces were, he realized that there's a problem. And the problem is, I'm going to just draw the problem. So you're doing Morse theory on the free loop space, which means you're solving some ODE in the free loop space. Okay, so there's some point, and you're going to look at some gradients. To actually understand what the problem is that Floer noticed, you want to translate this ODE to a PDE in M, which is just, well, this point it's point in the free loop space, therefore it's a circle. Okay, and this flow line now becomes a cylinder. Okay. And he worked out that this PDE that in M that you satisfy is some variant of the holomorphic curve equation. Okay, so I'm just going to assume people have seen the notion of a complex manifold and a map from a Riemann surface with a complex structure to the complex manifold. That's called a holomorphic map. So here I have a map from R times S1 to M. And in the best of all possible worlds, what would happen is you would look at this moduli space, and in its boundary, you would see this. It would be a manifold, and this is what would appear in the boundary.
Sorry, did you say what the almost complex complex structure?
I chose it, and there's a unique one up to contractible choice. You have to choose it. Every symplectic manifold has a unique complex structure. This actually comes down to some basic fact that the linear group that controls what's happening is sp2 and r, and this has a copy of un in it, and this inclusion is the homotopy equivalence.
But I want to say somehow the choice of complex structure is equivalent to the meaning of gradient flow.
Exactly. You have to choose some metric here. It has to be a good metric because everything is so delicate, and it comes down to this choice of complex structure. Thank you. Okay, so this is what you would like to see. But Floer noticed that you see something additional. We can also see this picture. Okay, so this is a picture that would make no sense in the free loop space. Okay, so it is a picture of a cylinder together with a sphere. Okay, and the sphere is mapping to our target, and this map again is holomorphic. And now I have to remind you that when we were doing things before, when we studied these moduli spaces, they were not the set of solutions to this gradient equation. They were the moduli spaces we had to mod out by R translation. Okay? So here we mod out by this R translation of this cylinder. It's fine. And now we have to mod out by two things. Some kind of R translation here, but also automorphisms of this map. Mod out by automorphisms of the map U. Okay? So if the map U is somehow injective, there's no problem. There's no automorphisms. But already, if you just let M equals S2, and you map it to itself by z goes to z squared, okay, then there is a automorphism group. In this case, it's Z mod 2, and more general, you get cyclic group automorphism. And you can have much more complicated configuration. It's not just a cyclic group. I can now start drawing some pictures where there's multiple spheres glued together, and this one has an automorphism, and this one has an automorphism, and then they're permuted by this, so you have some kind of wreath product of cyclic groups appearing. Okay. So if you encounter this, and you think that it's gonna be okay, maybe it's not so bad, you would maybe hope that you get an orbifold. Okay? I will maybe not define orbifold, at some point I will say some things. What it means is something locally modeled after Rn modulo gamma, where this is some finite group. You would hope that that's the case. And if that were the case, then life would still be kind of okay. As long as this gamma action preserves orientation, you can still make sense of some kind of fundamental class over the integers. You can certainly make sense of what it means to have boundary and so on and so forth. Okay? But unfortunately, that's not what's happening. Okay? The reason that's not what's happening is because there is a PDE behind the scenes. There is what's really happening is that you're looking at the space of C infinity functions from some Riemann surface to M. Okay? And somehow this space of C infinity function has some action of gamma. And on this space of C infinity function, there's some kind of vector bundle. I'm just going to call it F. This vector bundle measures the failure of holomorphicity. Okay, fine, I'll just write. It's omega 0, 1, sigma with coefficients in U upper star Tn. And it's just some vector bundle. Banach bundle, infinite dimensional bundle, whatever. Bundle. And the holomorphic curve equation is some kind of section to this. And, we know already from Morse theory that in order for us to satisfy the Morse-Mail condition, in order for things to actually have the dimensions we expect, we have to perturb. Things have to be in generic position. And now the question becomes, can we put this in generic position while maintaining the symmetries? Because the symmetry is a part of the geometry. And the answer is no. And this is what's called the failure of equivariant transversality. I want to give a very basic finite dimensional example, transversality, to explain how bad the situation is. So my example is going to start with this singular curve. Okay? Just compute. Okay. At 0, it has a singularity. Okay? And I can interpret this as a map from C2 to C. Okay? And you could imagine that this map from C2 to C is some kind of finite dimensional reduction of this infinite dimensional problem. And I mumbled some words about Fredholm, and Fredholm basically means this kind of problem admits such a finite dimensional reduction. You can choose one. And now my claim is that if you choose a cyclic group action on this, or rather you can choose a cyclic group action on the source and the target. I think you can do it with like Z mod 5. You can have it acting by weight 1 here, and acting by weight, I think 3 and 2 on these. Okay? And then this map will be equivariant, compatible with the group cyclic group action on this side and the cyclic group action on this side. And then you can ask yourself, can you make it smooth with this restriction? And the answer is no. And basically the answer is no is because the reason the answer is no is because if you look at polynomials and look at monomials in x and y of sufficiently low degree, none of them will be invariant. Okay? To get something invariant, you need something of degree higher than these things, and that's not going to allow you to kill the singularity of C. Okay? So the answer, I mean, this is not surprising if you've ever thought about something like this, but it occurs in the subject not because we care about groups, not because we care about singularities, but because we have no choice but to deal with it. Okay? Any questions before I continue? Yes?
Can you just maybe explain the group actions in this example a
Yeah.
little bit more? I mean, of course, Z mod 5 acts on C, that's good, but on here?
It acts on the two factors separately. Yeah. And on one of them, the generator of Z mod 5, let's call the standard generator zeta, acts by zeta cubed. So instead of rotating by 1 click, it rotates by 3.
Okay.
But that's another generator of the cyclic group of order 5. So you can that's also an action of Z mod 5, and here it acts by rotating.
Okay, and this is equivariant, but what was the issue that arose?
If you try to if you didn't impose the condition that the map was equivariant, you can just add some terms to this of lower order and make this smooth. Okay? That's what transversality says. You can always take something and make it transverse to 0. But now, the terms that are of lower order are not going to be invariant. Only terms you can write down have higher degree than this. And once that happens, whatever terms you added remains singular. Does that help? Okay. So now your hope to be like, well, all I needed to do is to just take manifolds and generalize them to orbifolds. They are now dashed, and you need to formulate a more general notion. Okay? So I'm going to define this more general notion. A proper, I will give the name that we're currently using, and I think by now the notation has stabilized. Proper derived orbifold consists of 1, an orbifold. So derived orbifold, let's call this X. This is like Blackboard X. Orbifold X. No Blackboard. 2, a vector bundle in the orbifold sense. I call the vector bundle T minus. It's supposed to be, you see this orbifold X has its own tangent space, and now we want some kind of negative part of the tangent space, which is the part that we're trying to cut out. The equation is going to arise T minus over X, and 3, a section of this vector bundle. T minus X. And I put this word proper here, so I'm going to write such that the 0 locus is compact. Such that SM is 0 is compact. So how do we get such things? Well, I'm asserting, in fact this is a theorem, that has long history going back to Fukaya and Ono, but of course they didn't phrase it like this. Okay, and then I wrote a version with McLean and Smith. And maybe just before we did it, there was an attempt to do some pardon. Okay? Many people thought about things like this. And basically, the point is that the kind of moduli spaces that Floer studied have this structure. So this is an abstract answer. In symplectic topology, this is a good notion. But what if you're not a symplectic person and you want a more concrete version? So let me give you a concrete way of constructing something. So G is a compactly group. Okay? And M is a manifold, not necessarily compact. Manifold. Okay? And now I'm going to put in some condition with finite stabilizers. Which means at every point, if you look at the subgroup of G that fixes that point, subgroup Gx of x given by G dot x equals x is finite for all x. Okay? And now, let's say that we have, I'm not going to use this T minus, I'm going to have just a vector bundle over M, and everything acts, G acts everywhere, and I have a section, and the section is compatible with G, and the zero locus is compact, then this gives rise to this. Okay? And in some sense, and it actually as a theorem, this is the universal example. Okay? Orbifolds are locally modeled after quotients of manifolds by finite groups. It is not possible to, in general, to make them finite quotients, like finite groups, but it is also always possible to do so by doing it with compact groups. So this is what you should have in mind if you are not comfortable with the notion. And I will kind of go back and forth because it's somehow much easier for me to talk about these people than to talk about. So now what I want to say is that, it makes sense to talk about, we can study.
But sorry, can I ask a question?
Absolutely.
Yeah. So, but we are always lucky that the group of symmetries is always finite here.
So in symplectic topology, the group of symmetries is always finite.
Yeah. Okay.
That's what it is.
Sorry.
It's since you're not, it's related. It is related, and in fact, not only finite. It's always built out of cyclic groups by this very concrete. What did they call it? I remembered the word when I was standing here, and I forgot. Wreath product construction. Okay.
Because you kind of have this.
Yeah. There's a cyclic group associated with a small one, and it rotates around. Anyway. Yeah. Okay, so we can study derived orbifolds with boundary. Exactly the same as before. Yes, go ahead.
It's just because you started with the Floer and you said that like for everything to happen you have to have manifolds with corners.
Yes.
But when you're like in the Floer case, like proving that your manifold like have manifolds with cornering the computation like a type of gluing, right? Which should be really hard.
It's really hard.
No, I mean like so you're saying that you have it for dimensions greater than 1?
Yes.
Oh, interesting.
Yeah, we can do it with dimension greater. It's very hard because you have to make it smooth. It's very delicate, but by now we know how to do it. We've built a universal base, and then we just do the gluing over that universal base, and then we build a smooth structure using that. There's some.
Because in the spherical case, you should only need the case 0 and 1 dimensional, right?
No, I would more say if you're doing ordinary homology, you only need a 0 and 1 dimensional case.
Right.
But if you want more general things, then you need a higher dimensional. Okay. So we can study derived orbifolds of boundary. That just means, X has boundary. Okay, and then everything restricts. And so there is some kind of naive definition. So we can kind of naively define some kind of orbifold Bordism group, a derived orbifold Bordism group, to be the Bordism group of proper things, okay, up to and killing the things which are boundaries of things which are one higher dimensional. Okay, so generated by equivalence relations of proper derived orbifolds, mod boundary. But that is the wrong notion. The reason that's the wrong notion has to do with like where did the question come from? The question came from understanding this this moduli spaces. And these moduli spaces, they're really most naturally cut out by some infinite dimensional problem. Okay? And I only produce the finite dimensional thing by a choice. And there are many ways of taking this infinite dimensional thing and approximating it by a finite dimensional manifold and a vector bundle. So the correct notion requires us to allow to also mod out by what's called stabilization. So stabilization just means, so if E over X is a vector bundle, let's call this pi, okay? Then I can take, so we can replace X by the total space of pi, so total space of E, and we can replace T minus X by the pullback, I'm going to write it, of T minus X, direct sum E. Okay, so I add E to my total space, and I add E to this negative part. This negative part is sometimes called the obstruction bundle. And then you replace S by the direct sum of S with the identity. Okay, I'll give an example right now. Okay, so this might be slightly mysterious, but it's a natural thing to do because I want to make sure that if something is transversely cut out, it's equivalent to the problem which cuts it out. So the toy case, and in some sense it has most of the idea. The toy case is you just take a point. Okay, this is a zero-dimensional manifold. And now I'm going to stabilize it by V is just R. So here's R. Sorry, did I call it V or E? E. E over there. It's R. It's a point sitting inside of R. Okay? And now, what I'm saying over there is, well, the vector bundle, let's say before it was nothing. So now we have to add the same thing. Okay? X is a point. T minus X is just 0. So it is R. So I need to add, so I now need to add a copy of R to my obstruction part. So the new T minus is now R. And this section, this is the new section. And what I see is I have a problem that's now I have made my space one larger, but I made one dimension larger. I made my vector bundle one dimension larger. I made a section which in this case is transverse to 0. Okay? So I say I dictate that this derived orbifold, which is R S equals the identity, should be the same as 0.0. Well, 0, there's no section you can write down. You just force this in. It's forced to you because you would like to know that when you get manifolds, you get the right answer, but also because reducing this infinite dimensional problem to a finite dimensional problem requires choices, but up to the stabilization procedure, they're all the same. Okay? There are people who do, derived schemes, derived C infinity schemes that would be, of course, be quite horrified by my definitions, but there should be equivalents. And the reason that I give them like this is partly because issues of smoothness for us are very, very hard to establish. So it's much better to have something that's more topological and flexible. Question? Okay, yes?
So I think I see from your stabilization process why if you have a transverse section, then its tubular neighborhood is the same as the zero locus.
So first of all, that doesn't even require, yes, absolutely, yes. That tubular neighborhood is the same as zero locus, and the tubular neighborhood is the same as the whole space because in the notion of cobordism, there is no compactness property on X. There is only a compactness property on the zero locus. So if you have some okay, happy? Yeah, okay, let me do it. So if you have something like this, and the zero locus is that, okay, then that is actually cobordant. Let's do it. To this. via some cobordism which is actually not compact on the whole space, but I don't need it to be compact on the whole space. Okay, so now we have some group, okay? Some group that nobody has seen before. But it's not just a group, okay? So this, derived bordism group is in fact a ring. By multiplication, by product of manifolds. And it's not just a ring, it is in fact the homotopy groups of some commutative ring spectrum. Commutative ring spectrum. Now, that all sounds very nice, but actually, if I'm 100% honest, what I've currently defined is 0. Okay? Currently, this is the 0. And the reason this is 0 is very simple. So it's a ring. Okay, let's believe that. So since it's a ring, it has a unit. And the unit is obviously the point. But the point, remember I have this flexibility. I'm really thinking in terms of orbifolds, so I can just represent something as a quotient by a finite group, okay? As long as that quotient is free quotient. So this point is the same as 2 points with a free action of z mod 2. Okay? But 2 points with a free action of z mod 2 is the boundary of an interval with an action of z mod 2, and well, we're done. We just showed the point is 0. Okay? So this group is trivial. So now I pay the cost of the fact that for the last lecture and for this lecture, I've been saying nothing about orientations. So we have to say something about it. So instead of saying something, okay, we can just now say something on orientations. So orientations, the natural way to orient things is to, so the natural, because of stabilization, the natural notion of orientation is on Tx direct sum T minus x. Okay? So really this shouldn't be direct sum, it should be like minus. Okay? Like the formal difference between the tangent space of the orbifold of the derived or underlying orbifold, and this what I said the words before. This is what I call the instruction. Okay. And now you can do whatever you want. You can, for example, formulate what it means for it to be oriented in the classical sense. SO orientation just means that these two vector bundles have coupled orientations. Okay? If this is the Mobius band, then this needs to be the Mobius band. Okay? That's all it means. U orientations would be complex structure, i.e. stable complex structure. Well, it just means that this formal difference has a stable complex structure. That's actually a delicate thing because there's a question of like, what are you allowed to stabilize by? So I would say, now I'm just going to hide that under the box. So we have stable. Stable complex structure on the formal difference after stabilization. But because stabilization itself is part of our tools, you can then stabilize enough so that this one has a stable complex, this one has a stable complex structure, and this one is a stable complex structure, and they stabilize further so that both of them actually have complex structure. It's a kind of standard thing to do. Lastly, framing, or stable framing, just means these two things are basically identified up to some trivial factor. Up to trivial something. Okay, so yes.
What's the difference here between a formal difference and a formal something? Like, I don't understand what that's defining us. Exactly what that means.
Honestly, for these things, it doesn't make a difference.
Okay.
It doesn't make a difference.
And why do we change it? Go ahead.
Well, I mean, so the formal difference is what you should think of as the actual. The formal difference is a dimension, which is the dimension of this minus the dimension of that. Okay, that's the dimension of the manifold you would have gotten if you could have achieved transversality. Okay. So that's the first thing to remark. So
you're finding this on the should sound. Yeah.
So this problem of things being equal to 0 disappears when you pass to any of these things. And in fact, we know that you can do you can count with rational coefficients. So the only thing we know in complete generality in the case of SO, without using kind of heavy machinery, so for SO, we know that there is a map to Q from this Bordism ring. And what does it do? Which on point mod gamma has output 1 over the cardinality. We know this map exists. But beyond that, we know very little in the SO case. So what I want to explain in the last 20 minutes of my lecture is the following, is the statement of some ideas behind the proof of the following theorem, which I recently proved with Xiaoyun Bai. And it says inclusion of complex cobordism I think of manifolds into complex Bordism of derived orbifold splits, as in it's split injected.
Should I
Yes.
give you a map to Q? It's Euler characteristic when everything is sort of manifold in Q.
Yeah, so here, we tend to just throw out all the higher dimensional moduli spaces. The map to Q is basically, because somehow, just like I said in the beginning, in this Floer business, when we do ordinary homology, we only look at things of dimension 0, we count them, and using dimension 1 to prove d squared equals 0. And then, so that's what this is. This is the whole rule, and everything else basically goes to 0.
Can I ask you another question? So,
Yeah.
So you know what in the SO and U cases it's not 0, but is it 0 or not in the frame case?
Is it 0 in what?
It's a frame for a frame case.
That sounds implausible because it's a module over it, probably.
Okay, sorry, yes. Yeah, sorry.
Yeah. Any other questions?
So in the framed case.
Yes. Nobody
Okay.
studied it. So you can ask.
Questions anyway.
Yes.
Do you get a map to something kn local by taking kn local?
Yes, it will probably factor through the U case. I mean, you can take the K in local thing, yes. But the question is, what is it going to compute?
I was thinking about this map, right? Like this notion of the thing that sends point
Yeah.
mod gamma to 1 over
Yes.
gamma, that
Yes.
thing has generalizations.
Yeah.
As I know you know.
Yes.
And
But
I'm
I
asking
know
if
them
these
coming.
things-
I know them coming out of MU. Are there really maps from the sphere that don't factor through MU?
Yes.
Okay, we'll talk about it later, which probably means next time I visit. Yes, I have not studied it, and it would be interesting to figure out what's going on there.
Is the sphere spectrum split up?
Well, that's a question for you. Our proof does not say anything about this. Any more questions? Okay, because our proof by the standards of statements like about about generalized cohomology theories in the current day is insane because it is completely geometric and uses resolution of singularities and characteristics zero. Okay. So what's in fact the proof is a proof as cohomology theory. It's really proof of splitting of spectra. But I'm just going to focus on coefficients. So the proof means, the statement means, given a derived orbifold X, okay, we can produce a manifold stably complex, again, which is stably complex. So this I'm going to stop saying it because from now on, that's going to be the assumption because I'm trying to explain this. Okay. We can produce a stably complex manifold. Let's call it M of X. Okay. And if this X, which again I remind you is an orbifold together with a vector bundle, together with a section, happen to be if X equals M0, 0, okay, you just get the manifold back up to Bordism, but in reality you literally get the manifold back. Okay? And this notion is compatible with stabilization, and this notion is compatible with Bordism. Okay, that's the statement. Okay, like so it's just an actual concrete statement. Of course, if you prove it using homotopy theory, that is still what you could conclude. Okay, but probably not. You get it on the nose back. It's very much harder to do. Okay. So what I want to do is I want to explain. So the proof has two parts. One part that is easy to understand and somehow could have been proved by anybody who asked himself the question, like in the 70s. And a second part, which is very delicate and uses some work of Fukai. So first I need some notation, so I stopped doing this. Nothing has any notation. So I'm going to write omega for complex Bordism. Okay. I apologize. I'm going to write U. Okay, this is Milner's notation, which was abandoned later. So I'm going to write U for complex Bordism. I'm going to write U orb for complex Bordism of orbifolds without this derived stuff. No derived stuff. And I'm going to write some derived orbifolds for what we've been talking about. Okay? And there's an obvious map. Every complex manifold is a complex orbifold. And there is an obvious map. Every orbifold, and everything here is compact. Every orbifold is a derived orbifold with a trivial vector. Okay?
Can I ask a question?
Absolutely.
What did the word derived mean? I just realized that.
So the derived part was adding this vector bundle. And the idea is you're trying to do derived intersection between the zero section and a transverse section. And you cannot make it transverse, so instead you just remember the data of the germ of what you're trying to do. And if you're doing algebraic geometry, you would actually just run with it and just try to do it in some reasonable way. But in smooth topology, I feel much more comfortable just remembering the vector bundle and knowing that I can stabilize. Okay? Now, the statement is that each of these things. Okay. That's how the proof goes. Okay? So, how am I going to do this? Well, I'm going to think about the simplest possible situation. The simplest possible situation of such an orbifold is maybe like C2 mod cyclic group of order n. Okay? Acting linear. So this is going to have, if I do this correctly, I'm sorry. Inverse. So if I do this correctly, this is only going to have one singularity at the origin. But I'm a simple-minded person. I can just blow up. Maybe the blow up doesn't resolve singularities, but I can just do it again. Now, if you've ever been in a talk about resolution of singularities, it will tell you until singularities disappear. It will tell you will learn that if you do this naively, you can be in a lot of trouble. Like you can go in some cycle. Okay, that doesn't happen with singularities arising from group quotients. You can just naively, this naive strategy works for V mod gamma and action of finite. Okay. Now you could say, okay, fine, this is the world of complex geometry, there's no problem. How am I going to use it? I have stably complex manifold with some kind of structure. So life is very delicate. But in fact, it again doesn't matter because, well, first of all, if it was just one point, you wouldn't worry about this. You would just say, there's no obstruction near this one point to making my stably complex manifold into an actual complex manifold and using holomorphic geometry. Okay? So if it's instead not one point, but maybe that there is some locus where the stabilizing group is non-trivial, and generally, if I have some kind of locus, x gamma inside x, okay, so I apologize. So let me put myself in a situation, generally, if, let's say gamma acts on M, okay? And so this is some kind of manifold with stable complex structure. Okay, and I look at the stabilizer of the stabilizer of this group. Sorry, I look at the locus which is stabilized by this group. Okay, then what I'm going to see is in the normal direction, I have a complex structure. Or I can basically have a gamma representation with a complex structure. Okay? Because this is like just some kind of tubular neighborhood theorem. Okay? The difficulty of making an almost complex manifold complex is all about the global topology and trying to go from chart to chart and making everything is consistent. I'm not trying to do that. I'm not doing anything along the dimension, along the locus of the fixed point locus. I'm just worrying in the normal direction. Well, the normal direction is tubular neighborhood theorem. That's not a problem. Okay? So then you just do that. Okay? The hard part now is, okay, well, gamma is a group, so it has some subgroups. Okay? So now you need to do things inductively. Okay? So, but this is not very helpful. So, and do this. Okay. It's really shocking to me that this proof turned out to be so simple. I think we do it in about 10 or 15 pages because we give a lot of detail, and then you have to prove that this is compatible with cobordism, but it's kind of obviously compatible with cobordism because you just need to make sure that this strategy for blowing up is some strategy that just only uses information about the representation, uses nothing more. Okay? You're not allowed any choices, because if you did any choices, then you would be in a huge amount of trouble when you try to say, oh, well, I've done my procedure for this one and then my procedure one, and we go between them, okay, and they've both been resolved. Okay, well, how do I know that my procedure that I chose here and I chose here actually extends? Okay, that's not, if you make choices, it's not clear. But this naive process doesn't require choices. You blow up, you see a projective space. On that projective space, there's now some induced representation that has smaller groups, just continue. Okay? Questions?
So this is not the context where, I mean, your group here is arbitrary, or?
Any arbitrary, any finite group.
Okay.
Yeah.
But for, well, complex. Sorry, okay.
The representation is complex.
Oh, sorry.
Yeah, I don't know.
The groups that are arising in practice are much more special, but you're not using anything about.
I'm not
structure.
using any of that.
All
And
right.
it's actually strange that we're not using any of that, and somehow what we should do now that we have this kind of huge hammer that solves something is to go back and think about like what was the geometry and how much did we need and we can get better. But at the time it felt better to just think about it like what's the most we could do? And that's what we can do. Yes.
So when V is C2, then there is some interpretation of the resolution of singularities in terms of the gamma fixed points, a certain Hilbert scheme. In general, is there such an interpretation?
I don't know such an interpretation in general. I think this is something that tends to be very special to like SU representation, and we don't have that. Yeah. So here, I know we don't. But I'm literally saying like if you just think about, we wrote it up, but if you just for yourself, you go back home and you think about having a complex group acting. I blow up. I'll see a projective space. Okay, it's an exceptional divisor. It will have an induced representation, and I'm just saying things are going to become simpler as you go on. So, questions?
Basically, the restriction that you have is just that those are solvable groups, right? Like that's really this.
I didn't use any solvability.
No, I didn't say that. I'm saying if you would have decided.
Are you telling me like every solvable group is
being a solvable is the same as being a subset of brief cyclic, right? That's,
okay. Okay, somebody who knows some group theory. Good. So I think I'm going to continue. I don't have that much time. So I want to talk about the much harder second step, which is this one. So part of the reason that this is much harder, there's many reasons why this is much harder. One of the, like you should almost not expect it to work. I want to point out something that I haven't explained yet, which is that manifolds, they only have positive non-negative dimensions. Okay, orbifolds also only have non-negative dimensions, but these objects can have arbitrary dimensions. So what is the dimension? So the dimension of X is going to be the dimension of X minus the dimension of the of this negative tension part of the tension space. I said there's something else. So the claim, and we can also prove this, is that this du orb is non-trivial in negative degrees. So why is that? There's a very simple case for one to think about, which is just a completely stupid case. Just take a finite group gamma, and let's pick some representation of it with with kind of no non-trivial summit, with no trivial summit. And now build this following derived orbifold: a point V, a point with this gamma action, trivial gamma action, and the zero section. So you're basically thinking of V as a vector bundle over a point, and you're saying that the origin is a section that's gamma invariant. Absolutely, the origin is fixed. But because I picked a representation with no non-trivial summit, there's no way to move this away from the zero section. And in some sense, a generalization of what we prove tells you that this also is non-zero, and you can kind of pick it. You can pick out a large piece of the derived orbifold mortism ring, this one, consisting of anything that looks like a complex manifold. Here, replace this point by a complex manifold. And that will be its own summit that's separate from everything else. Okay. So that's, again, some kind of surprising statement about the structure of this thing. Good. So how does this step go? This kind of a splitting from the derived to the orbifold. I've already told you that you cannot expect the zero locus to be an orbifold. But what you do is, but in the proof, so the example of x cubed plus y cubed shows that we can't directly produce an orbifold as a zero locus. So what's going to have to happen is we're going to have to use resolution of singularities on the zero locus. But which zero locus? There's so many. Everything is invariant under perturbation. You can things depend on Bordism. You should allow yourself some perturbation. And the idea, which goes back to Kai and Ono, they were thinking about it to try to produce z-valued invariance, not Bord z-valued invariance, is make S as transverse as possible. I'll come back to that in a second. Using only complex polynomials in the normal direction. So what does that mean? So first of all, remember here the analysis, the key point was to think about the fixed points. And in the fixed points, what I have is a representation. And even though I'm in the almost complex setting, I can assume that that representation is actually a complex representation. The failure of transversality in the equivariant case always has to do with fixed points. Okay? If things are free, then there's no problem. Because if things are free, you just take the quotient to make transversality downstairs. There's no room downstairs. And then you pull back up. Okay? So it's always having to do with the fixed points. So, i.e., if W is a local model for the normal bundle, and about W is kind of representation for the normal bundle of some fixed point stratum. So we can just we're looking at maps from W to V, and this is some model for the normal bundle. These are both gamma representations. And what I want to do is I'm looking at all, let's say, homomorphic or algebraic. And now the claim, which is what I started with this example, is that, if you allow yourself, once you reach a certain degree, the geometry of a generic zero locus doesn't depend anymore on how many more perturbations you take. Okay? So you can do the analysis here, and you can basically see once you, for this specific case with this Z mod 5 action, anything you could add to it, you can just change variables x and y and get the exact same singularities. Okay. So now comes the actual starting point of the whole project. So I was sitting at Columbia. And I was sitting in the algebraic geometry seminar, and Dan Abramovich came and talked about some functorial process for doing resolution of singularities. Okay? So remember, the issue is if you make choices, then you don't know it's Bordism in there. Okay? Here it was very easy. You don't need Dan Abramovich to tell you anything. You can just do linear algebra. Okay? But what's been done recently, since Hironaka's time, and apparently, actually, this was first done by, I'm sorry, I forget, so anyway, I'm just going to skip it. At time, it's been, so the resolution of singularity algorithm has been made functorial in the following sense. Has been made functorial as follows. So if you have a variety y, then you can produce y tilde over it, okay? Subject to the following rule. If y, you can do many more things, but the simplest thing, if y is an open inside y prime, then the resolution that you would produce from y prime would fit in a commutative diagram. Okay? So this is what it means to have, so there's some way of doing it for all y's, so that under open inclusion, nothing changes. Okay? Which means all choices are local and all choices are universal and compatible with each other. So now you just apply it to this, and in fact, you apply it to the universal fiber. Apply this to the universal fiber of all maps, of all equivariant maps from W to V. look at all polynomials, you can look look at all their zero loci. And there is some way of resolving their singularities, in a family, without making any choices, without knowing ahead of time what W and V are going to be. And then once you have that, using the tubular neighborhood of the normal bundle, you just pull back. Okay? And when you pull back, this resolution, the zero locus, which was singular, this x cubed minus y cubed, has now been smoothed, and it's been smoothed in such a way that it is compatible with coordinates. And that's the proof. Okay? And I will stop here. Thank you very much.
I have a question.
Yes.
Which I was wondering, I'm surprised at all the incredibly specific technical questions.
Sorry.
Pulling back, you started out through this really basic problem about, it's a specific problem, but it's a great problem. Arnold's number of fixed points.
Yes.
Then you have cotangent bundles. Great. So you're like, I want to solve that problem. Well, Floer tried to do this. You have this huge technical machinery, and now that doesn't work. And so what I would do is be like, well, let me rethink things. But what is this to try to make? Then you have a problem.
Okay, so let me give you a different answer.
The ratio of input to what you're going to get,
is very small. Sorry.
Small.
Well, the ratio is huge, yes. But let me tell you the honest truth. Let me tell you the honest truth. In fact, the reason that I put all this work is because we already had a proof with Blumberg of this extension of Floer's result to general symplectic manifold. It's a 360-page long paper. That proof uses chromatic homotopy theory in a highly non-trivial way. I don't understand chromatic homotopy theory. And so I was unhappy with this, so I thought I need a proof that I can understand. Okay?
When you plug this in, this bordism theory, does this tell you something about manifold, your theorem about derived Orbifold bordism?
Yeah. It doesn't say anything about manifolds, it says something about symplectic manifolds and diffeomorphisms and Hamiltonian diffeomorphisms.
And what does it say about that?
So since you really want, I'll give you
No,
So what it says is basically that the Arnold bound holds. Okay?
Okay.
That's what it says. It says. So what I didn't have time to explain is Floer could prove it in very special cases. Then Fukai Ono proved it with homology of M with Q coefficients. But the rank of the cohomology is smallest with Q coefficients as you vary over all primes. Okay?
Right.
So we wanted to get FP coefficients. Okay? And the proof that I gave with Blumberg gave it with with FP coefficients, but only using some machinery that.
Why do you want it with FP coefficient? Well, it just gives a better bound.
Right? It gives a better bound. Okay, that's another thing. But actually, if we had time, and I think we don't have time, maybe after the question session, I will tell you another problem that came out of this. Okay. A very nice problem about symplectic vibrations over S2. Yes, any other questions?
By the way, I'm not asking, I think it's a really important issue in mathematics.
Yeah.
I trust the smart people, that you're doing this for, but yeah, right. I mean, what is a 300 and whatever page proof?
Yes.
Right, I mean, there's these symplectic field theories, there's thousands of pages. No, they do this in number theory too, and I don't understand, what is your view? I think this is the most important thing.
Yeah, I think my view is like this. There are basic geometric questions that we don't know how to answer, and we only currently have one tool to do it. And so we should make sure we know everything about this tool. Okay. Otherwise, these basic geometric questions will just sit there and nobody will answer them. If I could not say that this is this conclusion, then I don't have much less of a motivation for doing this. Probably not enough to actually go through the problem.
But you thought this would be the quickest way?
I think this is the only way that I can understand why it's true. I wouldn't even say the quickest, because it was already written. The quickest is it's already out there. I don't have to think about it anymore. But I would say it's the only way that I can understand why it happened. That's what I would say. I think Tomer wants to say something.
So I just trying to understand just one step here, which is that, so the reason that you use this Fukaya-Ono is because this Abramovich and Temkin kind of situation, they need an algebraic
Yes.
thing. And so you first need to replace it with something polynomial so you can run their algebraic geometry.
Yes, absolutely.
Okay.
Absolutely. And there's some sense in which if you didn't choose the sections in this way, almost surely we would just lose control of being able to count. You have to use the data. Yes. This statement that I wrote about MU is false for MSO. The map has kernel. Sorry, that's for oriented boardism. The map cannot split because we know that something dies. It's really a fact about complex cobordism.
In the case of complex cobordism, like a specific question, how big is a kernel? You know? At least, like, can you
the largest group I've ever seen. Maybe it's a joke, but somehow I really mean like it has all the data of all finite sets acting on all finite groups of it. I just picked out something.
You have this negative and you can propagate.
In fact, there is a splitting of this map split. There's a map back to like the direct sum over all groups of a copy of complex cobordism. All isomorphism types of finite groups. It's really kind of crazy.
Wait, but Nikolai is asking about
co-kernel?
The kernel of MSO.
No, co-kernel to in a
He asked about the co-kernel of the map from.
He was asking about co-kernel.
Co-kernel.
Did you say? Did I understand correctly? There's a kernel for the map from MSO to.
Yeah. To all the two torsion.
All the two torsion.
But I know that as the kernel of the map into orbifold stuff. I don't know what the next step does. From orbifold to derived. Remember, there were two steps. Okay. Yes.
These constructions, do they produce a splitting? They produce a splitting in which category?
They produce a splitting in the category of MU modules.
MU module spectrum.
MU module spectrum. Yes. Yeah, I mean, we kind of wrote the proof, and it's like we wrote the proof of splitting in homology theories, but actually they produce a splitting in the category of MU module spectrum. I just didn't want to bother. The paper was long enough with the splitting. We don't have to add this to it. Okay.
Thank you again.